Hey everybody, today we're going to be talking about proportional parts of triangles as well as how we can use parallel lines to create those proportional parts. We're just going to jump right into our examples. So I have a triangle drawn for you, and what I'm going to do in that triangle is I'm going to draw in a segment that is parallel to one side. So there's one, and remember we mark parallel lines with arrows. So I've created a triangle with a line, and these two sides are parallel. And I'm going to go ahead and label my triangle A, B, and then C. And then over here I'm going to have E and D. So I have two triangles, ACD and ABE. And when you have two lines that are parallel like this, you create proportional parts. And I'm going to go ahead and write that proportion here for you. It's going to be that AB, so this side of the small triangle, over BC, and that's this little tiny segment right here. This ratio, or this fraction, is going to be proportional to the other side, so AE over ED. So before, when we had to figure out a ratio of two triangles, I would have had to have figured out the entire length of the big triangle, and then the length of the smaller triangle, and then the entire length of the large, and the entire length of the smaller. But now, in this unique case, if our segments or our sides are parallel here, we don't have to use the whole length of the largest triangle. We can just use each individual part. So this rule right here, if you have two parallel sides, then these sides here and here will be proportionate. So AB to BC equals AE to ED. And you can use this to find some missing lengths. For example, let's see here. I could draw on a triangle, and again I'm going to draw on my parallel side. There, and I'm going to go ahead and mark it with the arrows. If I labeled in this triangle that PT, let's see, so 7.5 was here, and then I put that this was 3, and then on the other side I put that this bottom part was 2.5, and I wanted you to figure out what X was. Because we have those parallel lines, we can go ahead and set up our proportions. So remember, we take the long side here, so 7.5, over the short side, so over 3, and then make it equal to the other side. So the long side on the left, that would be the X, over the short side on the left, so 2.5. And if you remember from the previous sections, when you have a proportion, you have to cross multiply. So you could go ahead and start cross multiplying. So you get 3x on the one side, and then you'd get 18.75 on the other. And then the last step is to divide by 3, and you get 6 1/4, so 6.25, and that would be the length of that side. So it's just proportions, just like we've done before. We're just using different parts of the triangles using the concept of a parallel line. All right. Now, the converse of that also works. So converse, remember, is kind of like the opposite or the reciprocal. So in this case, I could tell you that the sides are proportional, and that might look something like this. Maybe I tell you that this is 9 and 3, and maybe I tell you that this side is 6 and 2. Obviously not drawn to scale. So I could set up a ratio, so 9 over 3, and I want to see, does it equal the same ratio as 6 over 2? Well, if I cross multiply, I get 18 equals 18, and is that true? Yes. So if those sides were proportional, then that means that my segment here and here on the bottom and the top here have to be parallel. All right, so this is just going reverse. So here I didn't tell you they were parallel. You had to determine that by setting up your proportion. And if you get those same answers on each side of your equal sign, then that means it is parallel. All right, so it's just the same thing as the first slide, just reversed. Now, this should seem familiar from the last semester. We talked about mid-segment, but we talked about mid-segment within a trapezoid. Now we're going to be using mid-segments in a triangle. Mid-segment, if you have forgotten, it's just a segment with endpoints that are at the midpoint of a side. In this particular triangle, maybe I am working with it here, so X, Y, and Z, and maybe my midpoints of XY is here, and my midpoint of XZ is here. My mid-segment would just connect those 2 points. All right, and it's important to know that the mid-segment theorem states that mid-segments are parallel to one side. So this here, maybe I call it AG. AG would have to be parallel to YZ. So you could write AG, segment AG is parallel to segment YZ. Now what's cool about a mid-segment of a triangle is that there are actually 3 of them. So I could draw in another mid-segment as long as I have a midpoint somewhere on every side. And let me change the color here. I could draw a mid-segment from A to this midpoint, all right? And maybe we call that midpoint H. And so now I could say that segment AH is parallel to segment XZ. So notice that the mid-segments have to be parallel to one side of the triangle. And then lastly, there is a third. And it's just obviously from the other 2 midpoints, so from H to G. And on that one, then I would go ahead and say that HG, segment HG, is parallel to segment YX, and I could mark those as parallel. And you can mark more than one arrow, okay, 3 arrows, 2 arrows, that way you can distinguish what things are parallel to each other, so that's important. All right, so mid-segments, they are parallel to a side, and then the other part of this theorem is that the mid-segments are also half of the length of that side. So for example, I could draw in a triangle, a random triangle, and I could have the mid-segment drawn in here. And if I know that my length on this side on the left is 20, then that means my mid-segment would have to be 10. All right, so the mid-segment is half of its parallel side. And that's the mid-segment theorem. So a useful tool if you're trying to find some missing lengths or if you're needing to use them to set up a proportion. The next thing we're going to be focusing on, still with parallel lines, so we're going to be using those, but this time we're going to get out of the triangle for just a minute. In these scenarios, if you have multiple parallel lines, usually 3 or more, and then you have 2 transversals, what you can set up is another proportion. So if you have 3 parallel lines cut by 2 transversals, then the sides on those transversals are going to be proportional. So let me label these A, B, and C, and I'll label these intersections E, F, and G. You want to make sure you draw this in your notes. So because I know the 3 lines are parallel, then my proportion would look like this. AB over BC, so all of the sides on the left have to be proportionate to EF over FG. All right, very similar to the triangle, but we're just getting rid of that triangle shape and using the same concept. So proportions, really important, making sure you use the correct parts. And then, of course, we can go through an example where we use this concept to solve. So here, we're going to be given 3 parallel lines. They don't always have to be horizontal. They can be vertical or slanted. It doesn't matter. I've got 2 transversals. Now, this is kind of a variation of the proportional parts concept. We could set up a proportion. We could say that this over this, so 7x minus 2 over 4x plus 3, has to equal this one over this one. That's what we did in the last slide with our generic setup. And you could cross multiply and solve. However, there is a little shortcut to this one. If you know that 2 sides are congruent, so if I know that this side here and this side here are equal, so these are the same, then that means that these 2 over here also have to be equal. So rather than setting up a proportion, you could go ahead and make the 2 things that I circled congruent, and then you could solve. So you could say 7x minus 2 has to equal 4x plus 3. It will get you the same result. It's just going to obviously be a lot less work in setting up your equation. So proportion will work. That's what we did on this last slide. The left sides are equal to the right sides in your ratios. And then, or if the 2 sides here are equal, then you can make the other 2 equal. This concept does not work unless one pair are congruent to each other. So if they're not congruent, you have to go ahead and set up a ratio. That's really important. All right. And then if we solve this, subtract 4x over to the other side, we get 3x minus 2 equals 3. Add 2 over, we get 3x equals 5. So our x value is 5/3. And then I could go ahead and ask you to plug in to find a length, but in this case they just wanted you to solve for x. So you'd be done, and there's our final answer. The last part of the notes is going to be referring to the 3 special segments that can be drawn into triangles that create proportional parts. And I've got these 3 listed here. You're going to want to draw them into your notes so you have them to refer back to. We're going to be just setting proportions up every time, and what you should notice is that each rule is basically going to be set up the same way. So the only difference is you just have to be able to identify what special segment you're working with, because if you can do that, then you can set up a proportion the same each time. The first one we're going to focus on is an altitude. You've seen altitudes before, we just haven't talked about them in a while. Remember, an altitude is another name for height, and they create right angles, so that's important. And so I've drawn those 2 for you already. We've got triangle ABC and triangle JK. These are all going to be considered similar triangles. That's important to remember. And the altitudes are also drawn in here. BD is an altitude and JH is an altitude. They create those right angles. And all we're going to do is set up a proportion. So these rules say that the special segments are going to be proportionate to a set of sides ratio. So I'm going to write this out with my letters. So the altitudes BD over JH. So this ratio has to be proportionate to a ratio of a side. In this case, we'll do BC over JK. Keep in mind that I'm keeping the order the same. BD was the altitude of the largest triangle, so I started the side BC with the second ratio. Make sure you keep them in the same order or your proportion won't work. And then on the bottom, JH was the smaller one, and then JK also went with the smaller triangle. Then you could just set up an equation and solve. That might look something like this. Maybe I tell you that the altitude here, we don't know the height, and then this side here we've put 27. And then on the other side, we could put the altitude as 8, and the side here is 12. I just fill into my proportion, and I solve. And that would look like x over 27, x over 8. Oops. There's more than one way to write this. So x over 8 equals 27 over 12. Now, you could set this up a little bit differently and get the same answer, and that's going to be the same concept. This is just one of the options. If I cross multiply, we get 12x equals 216, and then divide by 12, you get that x is equal to 18. So that would be the height of this particular altitude. All right, so there's the altitude. The next one we're going to talk about is the angle bisector. Remember, angle bisectors are segments that split an angle into 2 congruent angles. All right, and I've drawn these in for you. I'm going to go ahead and label these a little bit. So this angle here is going to be congruent to this one, and then this angle here would be congruent to this one because those are angle bisectors, and my proportion is going to look very similar. I'm going to use the angle bisector on the top, so ZY over TM, so angle bisectors first, and then is going to be congruent to the ratio of some sides, so XZ of the first triangle, and then RT of the second triangle. And then just like the altitudes, if I gave you some numbers and variables, you'd plug it into your proportion and you'd solve. All right, so there's not much variation in these. You just have to know that it works for altitudes and angle bisectors. And then the last one is the median. Now, medians are a little different. We really haven't talked about those much. A median is a segment that is created from an angle to a midpoint. All right, and remember, midpoints split segments in half. So when I'm dealing with a median, instead of angles being split in half, my side is going to get split in half. So it's going to be HF and FS will be congruent, and then TN and NE would be congruent. And then again, just like before, set up your proportions. So have the medians in one ratio, VF over RN, is going to be proportionate to one pair of sides. Maybe I do VS over RE, and then we'd be done. All right, so you could solve, you could plug a bunch of stuff in. It just depends on what you're given. On a median, it might look something like this. Maybe the median they give you is that X is here, and these two sides are 6, and then maybe this segment here, obviously not drawn to scale, this is 21, and maybe these are both 14. So they may not mark them congruent, they may just give you the measurements. And then all you'd have to do is plug in your altitudes and then plug in a side. In this case, if you're going to use a side, you could use HS and TE. So get the whole length, and then that would work. So you'd use 12 and 28 to plug into your ratio. Multiple ways to do it, it'll get you the same answer. So if you have any questions about how to set up those proportions with medians, angle bisectors, and altitudes, let me know. But that's it for this section today. Thanks for listening.